So much. Hey folks, good to see you all and see some of your profile faces. Hope you're doing well and that things are going okay on this Tuesday. We're going to continue with our algorithms today. We're going to be talking about selection sort. Remember that yesterday we talked about bubble sort, which is one algorithm for sorting. We're going to be learning a number of them or covering a number of them over the next few class sessions. So let's go ahead and get into it. Um, Make sure to share my sound. Y'all have had a day to sleep a bit on our algorithm from yesterday. How are folks feeling about bubble sort and sort of working our way through the algorithms? Was it challenging? Does it feel better now that you've been able to sort of sleep on it and think about it a bit more? What do y'all think? Traveler says nothing is easy anymore. Was it ever easy? I mean, that's good. I'm glad at some point it was easy. But yeah, it is tough. Joseph says way better, like that. Nice. Right. Any other thoughts, feelings? Okay. All right. Well, we can continue on with selection sort. I would say in terms of like uh, challenge wise, is pretty similar level of challenge. We're starting off with some of the like quote unquote easier sorting methods, as you all have seen. They're not easy, but they're just a little bit simpler in terms of being able to reason through and ultimately code. So hopefully today will be another opportunity to solidify some of those skills. And again, as a reminder, we're not necessarily learning any new syntax, so we're just leveraging the syntax that we've already learned with JavaScript to build these algorithms. So I know it can still feel overwhelming at times, but remember, we're just kind of relying on the skills we've already been developing over the past few months. All right, so plan for today is to talk about selection sort, another version of sorting. We're going to explore selection sort, another basic sorting algorithm. You'll learn how it differs from bubble sort and its application in sorting tasks. So our goal is to implement selection sort and to analyze the efficiency of selection sort. So remember yesterday we talked about bubble sort as being a way where we're picking the largest number and bubbling it up to the top. The main process there was us comparing pairs of numbers and swapping them, and we kept swapping until the entire list was ordered. Selection sort, the goal of selection sort is to find the smallest number, move it to the beginning of our collection, of our array, and start to create in our array a sorted section and an unsorted section. And so each time we're iterating through the array, we're looking for the smallest number, adding that to the sorted section, and then continuing on again and again. So this differs from bubble sort, as I described. So bubble sort was sort of worried about the largest number, and our method is via swapping. That's the main sort of mechanism we're using, swapping these pairs. Selection sort also uses swapping. It'll swap different elements depending on which one's smallest, but we're trying to keep track of what the smallest number is throughout and continually moving that to our sorted side of our array. So they work just a little bit differently in terms of what the actual code will look like and what the process is for getting there. And again, as a reminder, this is different than the search algorithms we covered where we're trying to find a specific item. The goal here is for us to sort all of the items, and then perhaps afterwards we would do something like binary search or something like that. All right, we have another video here. I'll go ahead and get it started. If you all can hear it, please just give me a thumbs up in chat or on the video, and then we'll watch through this for selection sort.
Today we're going to learn selection sort. Let's say we're given the following array and we want it sorted in increasing order. How will we do this? During each iteration, we'll select the smallest item from the unsorted partition of our array and move it to the sorted partition. We'll keep track of the current minimum and current item with red and blue arrows. Let's get started. We always set the current minimum to the first number in the unsorted partition, in this case 2. We progress the length of the array looking for a smaller number. We find 1 at the end of the array and set it as our current minimum. We swap 1 and 2. We now have one item in our sorted partition. Moving on, we set 8 as our current minimum and scan the remainder of the array for a smaller number, updating the current minimum as we progress. At the end we find 2 and swap it with 8. We're ready for the next iteration. This time, 3 moves into our sorted partition. Let's watch the rest of the algorithm play out. Pretty simple. With each iteration, you select the smallest item that hasn't yet been sorted. Here's the pseudocode for selection sort. As you can tell from the code and the nested for loop, selection sort has a time complexity of big O of n squared, where n is the size of the array. Thank you for watching. Please subscribe and comment suggestions for future videos.
All right. Thanks, y'all. Thanks. Sorry for giving me the thumbs up there. So we saw there selection sort as a process where we have our, again, our sorted side, our partition of the array, and then unsorted side. And we could watch as we were tracking through and the algorithm was figuring out what the smallest value was and then swapping that to the current position. So we'll step through that a little bit more granularly now. So again, selection sort operates by selecting the minimum. And it says here or maximum. You could write selection sort to do the maximum and flip it. Either way, we're trying to find the largest or smallest of some number during each pass and positions it at its final place in the array using a single swap. So in this image right here, we have an array of 4 numbers. They are organized in reverse order. So what this algorithm would do is it would first go through and say, okay, what is the smallest number possible? In this case, it would say that 10 is the smallest, and it's going to move 10 to the beginning of the array. Once it's done that, we can sort of safely say, okay, 10 is already sorted in that very small list of one item, right? So at that point, we can move to the next item, and then once again, try and find the smallest element. In this case, it's 12, and then we then swap it with the current position. This creates now a side of our array that's completely sorted, right? Because we first found the smallest item, and then we were finding the second smallest item. We continue to follow that process until everything is either swapped correctly or is already in the right place, and we end up with the sorted array. All right, so we have a nicely complex description here of the time complexity. I'll sort of briefly go through this, but there's more information here if you're deeply interested. So the time complexity here, selection sort has a time complexity of O of n squares. That's the same as bubble sort, where n is the number of items to sort. This is because the algorithm goes through the list multiple times to find the smallest item and place it in its correct position. So a little bit further of a description here. So for example, for the first item, it checks all other items to find the smallest, making n minus 1 comparisons. Just to look back over here, remember, so we're saying n is the size of the array. That's the size of our input. And so when we're trying to find the first item, the first smallest item, let's go back one more. There we go. It needs to search through every other item besides the first, right? We're searching everything else, saying is anything smaller than this first item. So for the second item, we do the exact same thing, except now we have one item already sorted. So we can exclude that. So now we're doing n minus 2, so on and so forth until the entire array is completed. This ends up getting to a situation where you are approximately sort of this little representation here, which is approximately n squared for large n. So remember, with big O, we're often removing some of the constants, some of the least important values to try and get the truest sense of what's going to happen over time. I should say another way we can sort of understand n squared as well is that when we take a look at the algorithm, we sort of saw it briefly in the video, was that we saw two nested for loops, right? And that is a good sign that it might be n squared. So that's for the first thing I would go to, and then really take a look at the details there. All right, we just talked about selection sort. We talked about the process itself. So before we get into any pseudocode or code, let's try and step through an example here. So I'm going to do the same thing I did before. I'll hit view here, and I'm going to split the view here. We'll open up the file tree, and then I'll open up just our empty script, which is script 2, just so that we have something to type here overall. Okay, so remember with the selection sort, we start at the beginning, and we're trying to find the smallest number, and then we're swapping. So let's wake up my keyboard here. Here's our starting array. So we have 64, 25, 12, 22, 11. So our first step, we're at index 0, and that's a perhaps fancier way to say we're first starting by looking at this first number. Right? Our current smallest number is 64. And what I mean by that is our algorithm starts by saying, okay, as far as I know, because I haven't looked at any other numbers, any other elements in here, 64 is the smallest number so far in this array. Then we need to search through until we find the number that we're going to swap. So what number are we going to swap first within this array? Put it another way, what's the smallest number in this array? Awesome. Thanks, Joseph. Thanks, Tatiana. Thanks, Timo. Yeah, so the smallest number in this array is 11. So we're going to swap 64 and 11. So it means we end up with 11 at the very beginning and 64 at the very end. At this point, this side of the array, we could draw a little line here if it's helpful. The left side of the array that is already sorted, right? Because we found the smallest item and it's now the first position in that array. So perfect. That's great. We are done with that part of the array. In our next step, we're going to be looking at index 1. And Tatiana's on it. Yeah, so we're starting with 25. So current smallest is 25. The smallest number in the remaining array is 12. So we're going to swap 25 and 12. Oops, let me actually copy this down. All right, excellent. So, right, we start with 25. We look through the rest of the array. 12 is indeed the smallest number. So we're going to swap 25 and 12. Now the sorted partition moves up, right? So now 11 and 12 are in the right spot. We're good on that. So we don't need to worry about that anymore. All right, step 3, we're at index 2, which means we're comparing 25 again. So current smallest is 25. Smallest, oh gosh, if I can type it, smallest number in the remaining array is what? Tatiana's on it is 22. So we're going to swap 25 and 22. 22, 25. Partition has moved up. Now the first three items in our array are swapped. We can continue onward at index 3. Current smallest is 25. The smallest number in the remaining array is what? Of the remaining array, what's the smallest number? Yeah, it's still 25, right? So at this point, no swap is needed. Goodness. But we still move our partition, right? We're still saying, great, that's already sorted. We don't need to worry about that. At this point, we're at the last item. Depending on how you write the algorithm, you could technically do a check here. I don't know what you'd be looking for. 25 is, or 64 is going to be the smallest in our remaining array of one item. Or at the point where you get to the last item, you can say, great, at this point, it should be good. This is our sorted array. That's the process. All right, I've been talking for a bit. Any questions about this before I move ahead and pass it over to you? Feeling good, feeling sensible. Like for some of these early ones, usually at this step, it's like, yeah, it seems fine. Seems okay, right? Until we have to actually write some code. But thankfully the process is pretty understandable. I would say this to me feels like a very human process too, of sorting like a list. It's sort of like scanning through what's the smallest one. Okay, let me put that in a particular spot. Let's scan through again. What's the next smallest one? Some of the other sorting methods we'll look at feel very strange. They feel like very complex, but this one I think feels pretty approachable in some ways. All right, excellent. I don't think there's a second one here, but I think because we have time anyway, I'm going to give you all a second array to work through. I want you just to follow the same process that we just did, um, and step through this. Just do it on your own, and we'll give you a few minutes to do that. I can follow up afterwards. We can just talk through some of the iterations of how things are going to look, um, just to get some practice here in the idea itself. So let's put out a new array. Quickly, Joseph asked a question here, sort of maybe clarification. Every next iteration, we start at the next index and not at the beginning. Correct. Yeah. So whereas with other algorithms, right, we might be starting at the beginning every single time. In this one, we're restarting sort of one ahead at each step. Yeah, good call. All right. No better random number generator than a bunch of humans. Everyone, share one of your favorite numbers between 0 and 100. Let's do it, you all. Work out those fingers. So anyone have any favorite numbers between 0 and 100? 17, 34. All right, we gotta get at least one or two more. We all got. Perfect. Perfect, perfect. All right, I will share this in our chat. Oh, Joseph's adding more. I love it. All right, I'm just gonna keep it going. All right, so there is our array. So I want you all to walk through the steps of ordering this. Perhaps for each step, something to do, you could follow this exact process we just did above, type out sort of what you need to. This is going to help as we're about to get to pseudocode here, right? Or at the very least, sort of keep a sense of what the different iterations of this array are when we're swapping things around. All right, I will give you all a few minutes here. I'll put up, we'll say 2 minutes on a timer. And then once we come back, we can step through this together. Go over to our array here. Oh, no worries. Thank you for not recording that last bit. Excellent. So let's go ahead and step through here. So we have our array here of 1, 2, 3, 4, 5, 6, 7 different numbers. Perfect, excellent numbers that you all have supplied. So here's our starting array. So our first step, we're going to iterate through this and try and find the smallest number here. What was the smallest number you all found in this array? Yeah, right. So the smallest number is actually the first number here. It's already sorted, right? So in this case, no swap is needed. Our algorithm's still going to step through each item because again, the algorithm doesn't know what's in the rest of the array until it actually looks through each individual item. So even though we can kind of just like scan this and it feels like we're kind of automatically taking in all the information, our algorithm does need to step through and actually understand at each step, is this the smallest? Is this the smallest? Is this the smallest? So that means our sorted partition at this point is our just the first item, but no swap was needed. All right, and the second step, what's happening? How would you all describe the second step here? What numbers are we swapping? We're starting with 34 being the smallest. Our algorithm is going to step forward until it finds the smallest number. Yeah, all right, excellent. Sorry, so we're swapping 34 and 19. This moves our partition, right? So now the first two items are here. And we swapped 34, oops, not 24, 34 and 19. All right, excellent. So we can step through here each time. And again, we're just finding the next smallest number. So our next smallest number we can find here is 23. It means we're going to swap 23 and 34. Our partition moves up one. So I here swap 23 and 34. Our next step here is where we can see here 34 is the smallest number. So we're going to swap 67 and 34. Our next step here is we start with 67. We can see 49 is the smallest number. So we can swap those two. And then our last step here, no swap is needed. These are already ordered, even though 67 is our current value. We look at 93 and say, great, that's not smaller. So we've slowly built up and adjusted this array so that all the items are sorted. All right, not bad, right? I feel like sometimes it's nice to like really step through these algorithms. Maybe it feels like a little maybe obvious, something like that. But we often, if we were to do this again as humans, we might follow a process like this, but it would not be as clear as we're doing it, right? We're just kind of looking for the smallest number, rewriting it. It feels maybe a little bit uh, more intuitive to us in some way, but being able to really describe what exactly is happening is pretty interesting, and I think makes it kind of interesting just to see how our thought process can be turned into code. All right, those are a couple examples there. If folks are feeling comfortable with the overall idea of what's going on. Now we're going to try and turn this into a bit. We're going to try it a little bit closer to code here. So our next step here is to write some pseudocode for this. You all are probably used to this at this point. We're going to start with some array. Assume you have an unsorted array of numbers that you want to sort in ascending order. Our range that we're first going to begin to sort on is the entire array. We want to find the minimum value, swap the minimum value with the first element, that current element we're at. And then here, this narrow down the range, the idea here is that we have that sorted part of our array. So the next iteration, in terms of the next set of numbers we're looking through, should be a bit smaller, right? It should be a bit smaller overall. And we continue to repeat that process until we are done with the algorithm. Okay, that is the plan. I'll give you all a little bit of time to work on this. Here's things that I want you all to accomplish. All right, so write out, oh, it's just text. I don't do this. Write out your pseudocode. Try and avoid specific code, but you can use coding concepts, for example, like repeat, init, something like that. And if you have time, provide some examples as well, and just sort of use your own pseudocode to follow along, make sure it makes sense. All right. Let's take, we'll say 8 minutes or so to write this out. The more detail you can write on this, the easier it will feel trying to actually write the code. So go ahead and get started. I'll add a timer up, and then we'll come back together at the very end. We can share some pseudocode out and take a look at the example that they have here. You'll have had let's think through it. Yeah. Anything that you all wrote down, we were like, I'm not, I wrote it out, it makes sense. I'm not sure how we're going to do that in code, anything that seems particularly tricky. Agreed, Tatiana. Also terrifying, but yeah, agreed. All right, any other thoughts? Sure, Jess is working on it. Yeah, fair enough. All right, well, I can share the pseudocode solution they have. Let's talk through it. And I'll identify some of the parts that I think are particularly tricky to kind of think through. And would love if you all have some additional ideas, please do share as well. All right, let me share my screen again. Sorry, one sec. There we go. All right, so here is the pseudo solution that our curriculum shares here. So goal of the exercise is to sort a list of items in ascending order. So they put here, so for each item in the list, assume the first unsorted item is the minimum. For each of the remaining unsorted items, if any unsorted item is less than the current minimum, update the minimum, then swap the first unsorted item with the minimum item found. And the list is now one item more sorted. So that is what they put together. Let me highlight some of the parts that I think are that we have to really think about in terms of how we're going to represent this. So right here, we say for each of the remaining unsorted items, I think here we'd think about how do we do that, right? How do we run a loop that is only going to run for some part of the array, right? Because that's what we're saying here. The first time through, we'll basically be looking through the entire array, every item but the first. Then we're going to be looking through every item but the second, every item but the third, right? So I have to figure out some way to keep track and to slowly shorten how many items we're looking through to compare. I think that feels pretty tricky. This as well feels a little bit tricky to me. We did this yesterday in terms of swapping, but in order to swap the first unsorted item with the minimum item, we're going to need to keep track of both of those values. That probably means we're going to need some variables here to keep track of the first unsorted item and the minimum item that's been found. So those are a few things that I'm thinking of as we get to the solution here. We can also sort of identify a few things that hopefully feel pretty approachable. So when we see this for each item in the list, for each of the remaining unsorted items, we know we're probably going to be using some kind of loop, right? Some kind of for loop or a while loop, something like that. When we're talking about assuming the first unsorted item is the minimum or minimum, this is probably going to be some kind of variable declarations. We're going to have to access elements to keep track of them moving through the algorithm. Some of the tools we might use to build this algorithm are probably going to be for loops, variable declarations. We have a conditional here, right? Those are kind of the different tools we're going to be reaching for. All right, any questions on this pseudocode before we move ahead, or any of the pseudocode that you all wrote that we can discuss? Okay, all right, let's move it along. So our next step here, if you were writing in script.2, you'll have a bunch of your previous writing here, but that's okay. We can just clear this out. So now we're going to go ahead and implement selection sort. We have some of the instructions here. I think instead of just passing this over to you all, let's try and work on it together. We can try and figure out some different steps and run through this, just make sure that everyone's on the same page. We can talk through how to get to that solution. Okay. Omar, thanks for sharing out your pseudocode here. I think this is great. Yeah, perfect. All right, so I'm going to clear this out. What I would do if I was you all, so I would follow along here with your code. And as we're gonna go back and forth here a little bit. So as I pass over to you, you can run the code, identify what's gonna happen, what the output is. Please don't just sit and watch me. I'm sure it's very entertaining. I hope to keep you all entertained, but we want to make sure you're learning everything that you all can. So go ahead and follow along with this. So our first step is going to be to set up our selection sort algorithm. And let's put together a few test cases here as well. So we have some examples, right? It says here sort an array of integers, sort an array containing negative numbers, sort an array that includes repeated elements. All good. Let's just go ahead and start with just one so we can make sure that our function is written correctly, that when we test it out, it's running, it's doing something. I'll grab our list of numbers that we created together here as our input. Excellent. So we have the frame of our function and we have a test case. When I run this, what do we expect the output to be? If I run it right now, what do we expect the output to be? Yeah, thank you, Omar. I walked through this yesterday, but it's a good reminder, right? Whenever we're writing a function, if we don't return any kind of value, we're getting back undefined. Let's not forget our basics, even though we're in complex sorting algorithm land. All right, let me go ahead and, sorry, I'm gonna go back over here and grab our pseudocode so we can copy that over. All right, excellent. So our first step here with our pseudocode, we say is to find, or rather, for each item in the list, what tool should I reach for to write some code that will allow us to access each item in the list. What syntax, what concept am I reaching for in order to do that? Several people are typing. Oh, y'all are too kind to me. It's making me feel so good. Yeah, we can use a for loop. We can use a while loop for each. We got options, right? There's a lot of different things we can do. For now, I'm gonna stick with a regular for loop, but if you are interested, we can talk about at the very end how we might switch this to other iterative tools. All right. So let's go ahead and set up our for loop. We'll just do the basic for loop while I is less than array.length, I plus plus. Cool, cool, cool. We can test just that this is working as expected. Just console log something out just so we can kind of see what's going on. We can see we indeed count through all the indexes for our array, which is pretty nice. All right, so we have some sort of iterative tool here, right? Excellent. Our next step while we're within this for loop is to assume the first unsorted item is the minimum. We want to assume the first unsorted item is the minimum. How are we going to do that? What code would that look like? We want to assume the first unsorted item is the minimum. Either what would that code look like, or what are we trying to reach for? What tool are we trying to reach for? What do y'all think? So remember from our process or our pseudocode and the process we were following, the reason we're doing this is we're trying to say, okay, the first item, we're assuming that's the smallest item. And then we're going to end up checking through all subsequent items and see if any is smaller. But for right now, we just want to assume that the first item is the smallest item. How do we do that? How do we get access to the first item? Yeah, excellent. Thanks, Joseph. Yeah, so let's write this out, right? So what we want to do is we want to declare a variable, and we want to just say, hey, the first item of it's going to be our unsorted item, but we can sort of think of this on our first iteration through. The first item, that's the minimum as far as the algorithm is concerned. So I'm going to say let min equals, and just a suggestion here is to do array at I. I like that suggestion. This is the minimum value. Okay. Let's go ahead and see just what we're getting. Make sure everything's working. Cool. This allows us to step through every single item within our array. Perfect. All right, from here, let's assume we got this right? We can always go back and change our code. So now we need to do for each of the remaining unsorted items. So first of all, what kind of tool should we be reaching for here? For each of the remaining unsorted items, what kind of tool should we be searching for? Yeah, right. Another for loop. It's almost as if this was written to kind of give you a clue, right? This is what good pseudocode does, is it helps you sort of say, okay, all right, I kind of know what kind of thing I'm hopefully reaching for. So let's set a new one. I'm just gonna set up the basic for loop here. I'm using J as our incrementer variable. Excellent. Now we want to search through the remaining unsorted items. The remaining unsorted items. So right now, within here, let's say I'm going to console log out min, and then I'll do array at J. Let's log that out. Whew, got a lot going on. So we have two for loops going on. You can see the output has already gotten kind of crazy. Notice we have some duplicates here. And currently we're also going backwards, right? So on our first iteration, the idea is that we are searching through most of the numbers except the current one. But in future iterations, we shouldn't actually be going through the previously sorted items. That's where we're hoping to get to. We need to just go through the unsorted items. So what do y'all think? How can we just go through the unsorted items? That is, we need to put it another way. How do we go through all the items after our current value? And what I mean by that is, let's say we're at this stage of our array, of our sorting, I should say, right? We've sorted 17 to 34. Let's just assume those are the smallest numbers. And then we need to start here, right? We need to start at index 2 here. What do y'all think? What can we do? What kinds of things do we need to do? What do we need to keep track of maybe? What are some values we should be looking to? All right, cool. I like this. So Asari is saying increase j by 1. Just is pointing out, say maybe set j equal to I plus 1. All right. I like that. So yeah, there's a couple things we could do here. This suggestion, we're setting it equal to j equals I plus 1. Let's go ahead and run that and see how that differs. Okay, that's shorter, right? So we're already at a shorter step. So what we're seeing here, and let me actually, I'm just gonna make a little space here so it's a little easier to see the iterations. Does that help? No, not really. Hold on, hold on, hold on. Hold on, hold on, hold on, hold on, hold on. Let's add it maybe right here. That's better. Okay, great. All right, so what we see here is on our first iteration, we're starting with the number 17, excuse me. And then we're going to compare every other item within this list. All right, we see we go all the way down to 93. Cool, perfect. Right, that's going good. On our next iteration, we haven't done any of the swapping yet. We haven't done any of the actually sorting part, but we're just trying to make sure we can do the iteration part correctly right now, right? On this next step, we want to start with 34, right? We're now looking at the value 34. I love it. So we're looking here, we're assuming this first value is already sorted, and then we're just checking every value after 34. And we see that right here. So 19, 6, 7, 23, 49, 93. Right, and then we continue to follow that process. This list gets shorter as we go on. Why is that? Because what should be happening is the unsorted partition, the unsorted part of the array should be shrinking in size step by step. So along the way, it should be shrinking in size. So this is pretty good, right? Right now, we're not doing, again, any of the sorting. We're not doing any swapping or anything interesting. We're just trying to figure out if we can iterate correctly over this. And right now, we are mirroring that iteration. Excellent. Any questions on this so far? This is like, we're already like 80% of the way there. We're like doing quite good. This is one of the more difficult parts of this algorithm. Omar doesn't have questions, but he shows up to show us his flaming. This is fine background. All good. Yeah, this is pretty tricky. I would say like this line right here feels a little bit like magic. The reason we can get to this step, right, is knowing that we have to start ahead of where we're at. So how we might describe this first outer for loop is this outer for loop, its job is to slowly carry us through and help us identify what the current item is, the first item of the unsorted partition. That's its job. The inner for loop, its job is to iterate through all unsorted items. That's the job we've given it. So with that, it makes sense that our starting point should be one after our current value from our outer for loop. All right. Cool. Cool, cool. Let's keep it moving. So now we're We're checking for each of the remaining unsorted items correctly. If any unsorted item is less than the current minimum, update the minimum. Okay. So we can do this, right? We're probably gonna need some kind of conditional here. We have an if statement. What's the condition that I want to put within this if statement? If what? If what is less than, greater than, equal to what? What's that going to look like? What do you all think? All right, I got a suggestion from Joseph here. So if array at j is less than min. Yes, we are checking if any unsorted item. So remember this for loop, its job is to look through all of our unsorted items. So if any unsorted item, that's going to be our array at j, is less than the current minimum. Right now we're storing that with this variable min. Update the minimum. Okay. So to follow along here, what this would look like is if this is true, if an item we're looking at is smaller than our current minimum, if we look at the output over here, this would be something like, for example, if 19 is less than 34. We're going to go ahead and reassign the minimum to equal that value. Okay. I'll add this log statement back in here. Let's go ahead and rerun this and see how this changes the output we get. Again, we haven't swapped anything yet. We're not actually doing any of the sorting. We're just trying to identify if we're getting some of these pieces right. So we run through here. Let me actually, sorry, let me move this just up to here. Is that the best place to do it? Maybe not. I think just the output we're getting here is a little bit interesting because of how we've sorted the array. All right, let's do it here. What could I do here to make this more complex? Let's do this. I'm going to swap 23 to this spot. I just want to see some variation here. Okay. It tells us something. Might as well. All right. So what we see here with this output, I just reordered a couple of the values in here. So we see here for the first iteration, we already know 17 is the smallest number, right? So we don't see any changes in the values here. For this next iteration, what we're finding is that we see this 2323, this 1919. This is giving us some clue that what we're doing is we're finding the a current value that's smaller than, a new minimum that's smaller than our current value. So we can see some values here change, which the idea is that we're reassigning some value to min. So maybe to make this more clear, I can say something like min before. We'll put min there. And we'll say current value, or no, that current value is not really it. Unsorted value. Let's do that. Array at j. And then I'll say min after. I'll put this inside of this if statement. All right, let's run it. So much output. All right, what we're looking at here now is we have min before, unsorted value, min before, unsorted value, right? This first iteration through, nothing's getting changed because 17 is the smallest. In this next iteration, so min before is 34, right? That's the first number here. Unsorted value that it's taking a look at is 23. And then we trigger this min after because we're swapping the values, right? So we're saying the new minimum is 23. That's what we're going to be using looking forward. We then have min before. We're tracking with that 23. 23 is the smallest. We come across 19. 19 is now the smallest. We use 19, we compare it to everything else. 19 remains the smallest. So right now, again, we're not doing any sorting at the moment, but we are appropriately reassigning our minimum value. Okay, so this is the code that we have right now. All right, so this next step here, and notice this is outside of the for loop, at least in our pseudocode here, is we want to swap the first unsorted item with the minimum item found. Now, here's where this is getting a little tricky because I don't know if we have all the information we need in order to do this. So if we wanted to swap the first unsorted item with the minimum item found, how are we going to do that with our current code? What we might want to do is something like, okay, so we're going to set a temporary variable, right? We did that yesterday with bubble sort. Set a temporary variable. We could set that equal to maybe array at I, something like that. But then what are we reassigning here? Right? Like what do we want to reassign? It's a little unclear. If we think of the situation where we have on our second pass through, we're going to want to swap 34 and 19. What are all the pieces of information we need to know in order to swap these two values? What's all the information we need to know to swap these two values? What do y'all think? I was asking you outside of sorting, and I said, hey, I need you to swap these two values. What information do you need in order to do that? What do y'all think? What do you think? What information do we need to swap these two values? Omar, you seem uncertain, but yeah, we need the index values, right? We need the indexes of these two things to swap them. And right now, we would just be storing the minimum value. So instead of storing the index, we're just storing the minimum value of like 19 or something like that, right? So it's not going to work as well. So what I would suggest, we can actually just create more variables here. There's a lot of different ways we could code this. I'm just going to change a min to, instead of being the actual value itself, to just being the index. That's the thing we're keeping track of. In order to get that to work, we'll have to adjust our code here. Array at min. And then when we reassign min, we're not assigning it to the value, we're assigning it to j. So now we're just keeping track of the minimum index, the index that represents the smallest value as we step through it. We're still doing that comparison. So it's not like we've lost the value or anything like that, right? We're still doing the comparison. We're just using that index. So now doing the swap starts to get a bit more straightforward. What we can do is we can say, okay, we'll set up a temporary variable. Let's maybe set that to array at I. We can then reassign array at I to equal array at min. And we can say array at min is equal to our temporary variable. One thing I forgot to put down here is we're just going to return our array at the very end and see what happens. So that is our swap step. I'll put that right here. All right, let's see what happens. Y'all, y'all, look at that. Look at that sorted list. Have you ever seen anything so beautiful? No, I don't think so, right? I think Dragosh was saying something about going to like a really cool temple in Kyoto. Not as nice looking as this. This is pretty cool. This is actually not a lot of code to get our sorted array in here, right? Actually not a ton. It's actually not a ton of code here. And these steps are pretty identifiable based on our pseudocode. So we have our overall for loop. We're looping through everything here. We define our minimum index that represents the index that represents our smallest value. Then we're going to search through all subsequent values that are part of the unsorted list. If we find anything smaller, let's go ahead and swap that out, right? So now we're holding on to the index of the smallest value. And then we perform our swap statement, and we just swap those values. Finally, we'll return the final array, which will return everything to the right spot. All right, y'all, what do you think? Any questions on this code? Anything feel surprising? Anything you're looking at that and you're like, how does that work? That seems like that shouldn't work. Any improvements you think we could make? Okay. All right. Cool, cool. All right, I'm gonna go ahead and I put this together earlier. I should do the same thing that I had done yesterday here, where I have another version here that just has a bit more text in it, just so we can kind of see this work as we step through the code. Okay, this is very similar. I'll get rid of some little optimization things I did here so we can really just be looking at the exact same code. I think everything else here is exactly the same. Yeah. Okay. And there's just a bunch of extra console log statements in here. Let's go ahead and run this so we can see us stepping through the algorithm. Okay, so again, it's the same code. We're just adding console log statements to just hopefully help clarify what's happening at each step. So we start with this array of 5, 4, 3, 2, 1. At the first index, and that's this index up here of our outer array, the current value we're looking at is 5. Right? We're starting at the very beginning, and we're saying that's the smallest item is 5. We then compare 5 to 4. 4 is less than 5, so we update our current value. And actually, instead of updating current value, let's say update minimum index. That's more precise. It's more precise. We compare 4 to 3, update minimum index. We compare 3 to 2, update minimum index. We compare 2 to 1, update minimum index. That brings us to the end of our array. So we swap 1 and 5. That leads us to our array looking like this. We've gone through this inner for loop, and then we go back to our outer for loop, and we increment by 1. So now we're at index 1 in our outer for loop. The current value we're looking at is 4, right? Because we're moving ahead in the array. We then check every value above. We compare 4 to 3, 3 to 2, 2 to 5. All those get are going to be, let's say, here. So 4 to 3, we update minimum index. 3 to 2, update minimum index. 2 to 5, 5 is not less than 2. So we'll swap 2 and 4. At this point, we actually end up with the sorted array, which is pretty nice. So you can see at the next iteration, we're comparing values, but nothing smaller. Right now, we have this step of where we're swapping 3 and 3. That's because there's no smaller value. So the swap still runs in our code and just does nothing really, right? Just swaps to the same place. And that happens again with every subsequent run. So we slowly step through and swap the values as needed. We can try a different array here. Let's try the array we put together as a group. Okay, and here we can see, again, the whole process. Sort of first step, 17 is the smallest number. So we can see we compare, make all those comparisons, but we're basically just leaving 17 in the same place. With 34, we can compare to 23, update, we compare 23 and 19. 19 is the smallest. We'll swap 19 and 34. Now we're at 23. 23 is already the smallest, so we make no changes. 34 is already the smallest, so we make no changes. We swap 67 and 49. That's it. And then we get to the very tail end of our algorithm here. No more swaps are needed. So that is our algorithm. That's how it works. That's what it looks like at each step of the process. There are perhaps a couple iterations we could make here to make things a little bit improved. We could, for example, add only go until the last item here, because at the very end, the last item should be sorted, so we could ignore that last item. We could do some kind of check to say, hey, if min is I, that is like if it's never been changed, or sorry, let me put it the other way. If they're not the same, that's the only time we want to swap. So we don't get this like swap 34 and 34. These are pretty minor adjustments. It's not going to be too different here. All right, any questions on selection sort before we take our break? All right, what's the feeling at the moment? Feeling good about selection sort? Feeling about selection sort? Feeling sad? Single tier? Single tier down? That selection sort? What do y'all think? Dragosh has a tummy ache. Oh no. Algorithms have been known to give you a bit of indigestion. It can happen. All right, got a thumbs up from Joseph. How about the rest of y'all? Hanging in there? Hanging in there like a motivational kitten poster? Just hanging in. All right. I do all these jokes and I hear nothing. So I hope y'all know I'm performing, I'm doing trying to keep the energy. All right, cool, y'all. Excellent. All right, well, let's go ahead and take our 10-minute break. We will come back and then we have a lab where we're going to implement selection sort with sort of a more real world situation. Oh, thank you, Veronica. I wasn't entirely fishing for compliments, but I appreciate it nonetheless. Just goofing with y'all. All right, excellent. Let's take our break. We'll come back, complete our lab, and then looks like we'll have a little bit of extra time as well. So if there are any other questions that you all have about this content or about perhaps some of the projects that you all are trying to finish up, I believe that's due on Thursday, if I remember correctly. Just anything there from our class that it would be helpful for me to maybe just chat about briefly, please let me know. All right, see you all in 10. All right, cool. Welcome back, y'all. We had a nice break. Oh, you hear me better now? I hope you all had a nice break. Let's jump back into it. So we have our lab. where we are going to apply selection sort in a more real environment. Share my screen here. All right. So what we're looking at for today, so we have our lab book collection organizer. We're going to implement the selection sort algorithm to organize a collection of books by their page count in ascending order. Given an array of book objects with properties title and pages, fill in the missing parts of the provided starter code to sort the books by their page count using the selection sort algorithm. So some of it is already set up for you all. We can see we have our two loops here. We've defined our minimum index right here. However, the thing that we're searching through is an array of objects. So we have to take that into account as we're doing our sorting. Everything else, though, should basically be the same. So the things you're gonna have to account for is when you compare the values, the things you are comparing is not just the element itself, but the element's pages key. And other than that, I think pretty much everything else should remain the same. So go ahead and give this a shot. We'll give you all a few extra minutes. I don't think this should be too much code added, but give you some extra time in case you want to take a look at the selection sort algorithm and are trying to apply it. You can write a few different test cases, maybe change around some of the page counts here just so that you can test out and make sure that it does indeed work. But at the very end of this, you should end up with all the books categorized according to the pages themselves. All right, any questions before we get started in this? Okay, I am going to stop sharing. I'll give you all, let's say, 8 minutes or so to work on this, and then I'll check in and see where folks are at. All right, welcome back, gang. How's it going? Folks need more time. Folks almost there, feeling close to implementing selection sort in this challenge. Where is everyone at? Omar says he's about to be done with his, so we could stop the Coco Melon songs. All right, I suppose that's fine. How about the rest, y'all? Where are the rest of y'all at? Or did everyone just mute us and now we're it's silent for you all. Dragish was hypnotized by the music. A little bit behind. All right, fair enough. We got some folks who are feeling good, feeling done, present, alive, sound on. Okay, much appreciated. All right, well, I hope you all are able to get to a good spot in that lab. I'll go ahead and walk through the solution that the curriculum provides. We can just talk through it. It has a tricky line of code in there. And then we can, I believe, start to kind of wrap up for the day. So let me go ahead and share my screen. All right. So here's the solution that the curriculum has put together for us all. So there's only a few lines that have been added here. It's not a ton. This first block of code should look pretty familiar to what we had done previously. So we're doing the comparison and checking to see if the current value is greater than or less than the new value in the unsorted list. So the only difference we really see here is that instead of just saying like books array at J and books array at minimum index, is that we're accessing the pages value on uh, on these objects that we're getting back from them, right? So it does add a little bit of complication here, but I mean, as you all can see, it's not too much, right? This allows us to sort by pages, um, which is pretty nice. And typically, you're not necessarily going to be working with just an array of numbers. You'll be working with a data structure that looks more akin to this, which is definitely cool. If the current item that we're looking at does have less pages than our current minimum, then we'll go ahead and swap that index and continue onwards until we reach the end of the array. Then we have our swap functionality down here. So we have this conditional statement, excuse me, where we're saying if the minimum index is not equal to I, that is like if it's changed at all, then we're going to swap these values. This is, I would say, a little overly clever, perhaps for where we're at now, but it is interesting. So if you all remember um, destructuring arrays, right? We could do something like const val1, val2 equals 1020, right? This would assign the values of this array to the values on the left over here. So that's what's happening here, is doing the same thing, but instead of declaring new variables, it's swapping those values. So we're swapping books array at min index, assigning that to books array at I, and assigning books array min index to books array at I here. So we're swapping those values. Kind of clever, kind of a clever way of doing this. But you don't need to do that. If that you look at that and you go, I don't like that at all. You can just do something like uh, books array at I here, books array at I equals books array at an index. Right, we could just swap it the way we're used to. Either way will work. The end result is, this is our before sorting, this is our after sorting. After sorting, we can see the books are in here. It's an array of objects still, but the page number is the sorting metric here. So that's how those get sorted. This is pretty useful. This is the kind of thing that we could see on a lot of different websites. For example, like with a products page on Amazon or any other shopping website, if you're sorting by price, size, color, this kind of algorithm could be under the hood, allowing that sorting to happen. What's nice as well about this kind of example is that we can see here that in this case, we're sorting by pages, but if we had other values within here, we would just need to change the keys here to be able to sort by something new, which is pretty nice. So there's a few different, there's a lot of different use cases for something like this. All right, any questions? Any questions from y'all on selection sort? We have a friend here wants to say hello. Go. Look at this guy. He's just really liking our classes. He's usually not so chatty. Does my microphone smell interesting? All right. All right. Any other questions from you all on selection sort? All right, Joseph says all good. All right. Anything else that you all have questions? I believe this is our last slide here for selection sort. Yeah, we're done with that. Omar, not true. My dog does not want to react better. He's working on it though. He's working on it. So he's getting there. Any other questions you all have about perhaps your projects, anything else that is stumping you at the moment that I could help explain as well? How are the projects going? Are you all already done, ready to submit, or already submitted? What are some of the last tasks you all have to do? Ooh, I see that several people are typing. People got some thoughts. Yeah, where are you all at with your projects? All right, vibes seem mixed. That's what I'm gathering from some of these responses here. It can't be that bad. It says almost done actually. Any tips on design? I mean, there could be a lot of tips on design. I think my biggest tip is to not forget that white space is important. Having a website that is clean and understandable is often better than a website that has lots of doohickeys and sparkles on it. You can always look to front-end frameworks for some good examples of clean websites like Twitter Bootstrap. Uh, there's often a lot of examples on those sites that showcase some really nice designs that are not too overly complicated. But glad you're almost done, Timo. Well done. All right, sounds like folks are bouncing around a bit. Hey, y'all, don't be scared to tackle these projects as best you can. I know it can feel like a daunting amount of work, but you all are welcome to, of course, ask for help in chat and elsewhere. And I hope you can find some enjoyment in it as well. Coding can definitely be challenging, but it can also be lots of fun, as long as you sort of allow yourself to be curious and entertained by the amount of errors and oddities that show up as you're coding. So hopefully you can find some time to jump back on some of these projects. All right. Well, it sounds like folks are sort of a bit all over the place. That is a-okay. So in terms of our selection sort lesson, there's no more to go through. We've gone through selection sort, did the lab. On Thursday, not tomorrow, on Thursday, we'll be talking about insertion sort, which is one of the last O of n squared sorting algorithms we'll go through. After that, in a pretty quick session, we'll go through some slightly more complex topics to round out our coding specific module and move on from there. So I think that's it. C1 folks, is there anything else you would like to discuss or share before we